Hello, everyone. Thank you for joining us today for today's EEA Education Series webinar. Today, we will discuss network bridges, transferring value to and from the Ethereum Mainnet and other cross-chain interactions. Today's call is being recorded and will be available to all attendees and the public on the EEA YouTube channel soon after today's presentation. The EEA enables organizations to adopt and use Ethereum technology in their daily business operations. The EEA empowers the Ethereum ecosystems to develop new business opportunities, drive industry adoption, and learn and collaborate with one another. We welcome any and everyone to join and become a part of our global community. At this time, we are pleased to introduce our moderator, Weijia Zhang.
Thank you, Brittany. This is Weijia Zhang. I'm from WanChain, a member of EEA, and also I'm co-chairing EEA CrossChain Interoperability Working Group with Peter Robinson. Peter.
Thank you. Yes, hello, I'm Peter Robinson. I'm from Consensus Software R&D. I work on CrossChain Bridges there, and I'm also co-chair of the EEA CrossChain Interoperability Working Group. So back over to you, Weijia.
Yep, thank you. And we have a very extensive topic today. So there'll be three main things. One is to discuss CrossChain bridges and CrossChain interoperability. And then we're going to talk about CrossChain bridges landscape. There have been many bridges recently built already. And we're going to talk about that. And then we're going to talk about EEA CrossChain Interoperability Working Group, the work that we have done. And we're going to have about 45 minutes presentation. Then after that, you're welcome to use chat to post your question, or even you can post the question earlier. And Peter and I will try our best to answer your questions. So we go to the first section about introduction to bridges. And when we say bridges, we mean CrossChain bridges. And there's three things that a bridge can normally do. First, a CrossChain bridge is connecting a source blockchain with a target blockchain, and it can transfer asset from a source blockchain to a target blockchain. We call it asset transfer. Of course, you can transfer ERC20 fungible token. You can also transfer ERC 721 non-fungible token. You can also transfer native token as well. So that is what we call asset transfer. And the second kind of transfer is the data and message transfer. This is to transfer arbitrary data and message from one blockchain to another blockchain. And then the third one, which Peter has been working on extensively, is to transfer commands. This is basically to do the CrossChain function call. So basically, from a source chain, you can call a function of a smart contract on another blockchain and achieve the actions on the target blockchain. And of course, this is very complex because you need to deal with finality, deal with security, a lot of things that need to be think through. So these are the three things that a CrossChain bridge can cover. And then we're going to talk about these during our presentation. And sometimes bridge can be named differently. It's sometimes called a blockchain bridge, sometimes called a CrossChain bridge, or sometimes people even just call it DeFi bridge or token bridge. Depends on what kind of asset or data they are transferring. And when you look at the type and topology of CrossChain bridges, there are several classifications that you can do. For example, here we can have direct bridge or hub-based bridge. And we're going to talk about that. And when you look at the topology, you can have a L1 to L1 bridge, or L1 to L2 bridge, or L2 to L2 bridge. I'm going to show some of the diagrams that shows the differences. So this is the difference between a hub-based bridge and a direct bridge. On the left side is a hub-based blockchain bridge, and all the blockchains that need to be connected will go through the hub. And of course, this is almost like a centralized server with the internet, while the other one is almost like a peer-to-peer transfer. For the direct bridge, you have two blockchains connected through bridge nodes, and these bridge nodes will just pass the data from a source chain to a target chain, and then the registration and the staking of the bridge node will be handled by an external bridge. Sometimes we call it coordination bridge or bridge blockchain. Then the bridge blockchain will not be in the middle of the asset and data transfer. So that's the difference between a direct bridge and a hub-based bridge. And when you look at the topology, today, when we talk about cross-chain, we normally mean L1 to L1, which is the chains, the blockchains such as Ethereum, Bitcoin, EOS, XRP, Polkadot. We connect these blockchains at the L1 level. And sometimes we need to have a level 2, which is the layer 2. And that is the connection between L1 and L2. Some people call it roll up, but some other people begin to call it bridge as well. So that's L1 to L2 bridge. And there's some similarities between a roll up and a cross-chain bridge. So I think it's good at some point to call these generic bridge that can be L1 to L1, L1 to L2, and then there is a need, I think this is coming up, it's a L2 to L2 bridge. Because of the improvement of performance and scalability, there's a more and more need to connect L2 with L2 without going down to the L1 level. And this, we're going to make this, the performance improve dramatically when we connect L2 with L2 bridges. And this could be asset or data as well. Yeah, and because cross-chain bridges are fairly new, a lot of people just see new bridge building up. There have not been extensive study on the criteria of cross-chain bridges yet. And we look at it, our cross-chain interoperability work group look at the criteria of cross-chain bridges, and we come up with 3 important ones, which is cross-chain security, and cross-chain decentralization, and then cross-chain scalability. And we're going to cover these criteria in the later section when we talk about the work of our working group. Now I'm going to pass this to Peter.
Yes, thank you. And so now I'm going to talk about the cross-chain bridges. Could you go to the next slide, please? Yep. And so we're actually going to talk about this set of bridging technologies. I know we had a slightly different set in the abstract, but things change very quickly in the bridge and cross-chain space. So, you know, this is the set that we've decided was the way to go. And I'll quickly pass back to you, Weijia, to talk about WanChain Bridge.
Yeah, thank you, Peter. Yeah, I think there are at least several kinds of bridges. One kind is atomic transaction, that all the transactions are atomic, and Peter are going to talk about with GPACT. And there are also trusted bridge, which means that the transaction may not be atomic, but the bridge nodes are trusted and decentralized and trusted, and that still achieve the goal of transferring asset and data from one blockchain to another. And I think we talk about bridge nodes having the function of transferring asset and data from one blockchain to another. And there are differentiations for different kinds of bridges with that bridge node. And WanChain is a kind of bridge that use trusted and decentralized bridge node to connect a source blockchain with a target blockchain. So we call that bridge node as Stallman group. So Stallman group is a collection of Stallman nodes that will connect source chain with target chain. And these Stallman nodes will detect events in the source chain to see if there is any cross-chain transaction happening in the source chain. Once the cross-chain events are detected in the source chain, the Stallman node will trigger action on the target chain, depends on the request of the cross-chain transaction. And then to ensure security, there are multiple of Stallman nodes forming a Stallman group, and using MPC, multi-party computing, we achieve the security for the cross-chain transactions. And for multi-party computing, basically, if you have 25 of nodes, you probably need to have at least 17 or 18 of the node signing each transaction in order to make it securely going through from source chain to target chain. And also there's another feature, which is to make a staking as a security feature for the bridges, because Stallman nodes, if you make it decentralized, there's a possibility for collusion. And in order to prevent collusion, we ask the Stallman node operators to stake a certain asset to smart contract. And also partners can also stake to the smart contract, and dedicated can stake their assets to the smart contract to secure the bridge. And this is to prevent Stallman node to collude to steal the fund while doing the cross-chain transactions. Yeah, and then there are 3 phases for each Stallman cycle. So basically, we introduce randomness to make the bridge even more secure. If you have a Stallman group working all the time by itself, then there's a chance that with time goes on, sometimes the collusion can happen. So every month there's a new cycle for the Stallman group. And then there are 3 phases. The first phase is for any node to register to participate. And at that time, they need to stake their asset to secure their bridge. And the second phase is to select the nodes and then do a setup for the nodes that take about 2 or 3 days. And then the third phase is for the Stallman node to start working. And the working cycle could be renewed. So you do not need to renew in each, do the manual setup in each cycle. You just say that you want to renew it for each cycle. Then that Stallman node can work just within the time you specified for the renewal. So this way, they are like 25 or 29 nodes operate as a group to secure the bridge, and there are also stakes to secure the bridge to prevent collusions. So this is one type of bridge. Now I'm going to transfer Peter for other types.
Thank you. And yeah, so another type of bridge, another company that's developing it is called ChainSafe, and they've developed a bridge called ChainBridge. And so with their system, they have, you can imagine you've got 2 blockchains, and their one is just between 2 blockchains. And so you have a source blockchain that you're trying to do a function call that's going to end up being called on the destination chain. So you do a transaction on that source blockchain and you execute some business logic. And then that's going to be saying, it'll have something saying, please call on this blockchain, this contract, and this function with these parameters. And so it'll call down to a bridge contract, which will emit an Ethereum event. And that Ethereum event can be proven to be part of a transaction that was part of a block. And so you have a set of relayers, and those relayers all observe that contract and note that that event has been emitted. And so they all separately sign that event, and then they put it onto that destination blockchain. And so once you've got enough of the signed events on that destination blockchain, so once you've got a threshold number, then it gets accepted, and then the information in the event gets executed, and so you have a function call happens on that destination blockchain. Next slide, please. Cello Optics is another company, or Cello is the company, and this is a bridge from the Cello blockchain to a range of other blockchains. And so this is a relatively very recent technology that has got some very interesting concepts in it. So you do the same sort of thing when you're generating that event. So you submit a transaction, business logic, you execute you say you want to do a function call on another blockchain, and so you have a bridge contract emits an event. You then have a testers that observe the events that are being emitted, and then they create all of these events, these messages, and put them into a Merkle tree. So a Merkle tree is a construction where you've got a root and then you've got branches that go down. And so they create what's called an incremental Merkle tree, where you add new messages, new values along the bottom of the tree, and then create a new root. So the root of the tree is calculated based on the messages or the information in the tree. And so each time you have a new message added to the tree, you get a new root. And so why this is important is that with that root 2, you can verify message 1, message 2, and message 3. So every time you add a new message, you create a new root, but you can still verify all of the old messages. And so this is useful because maybe you might have 100 messages might go by, and then you might just generate a new root because maybe this will give you scalability. So it's an interesting way of doing things so that you don't have to sign as many messages. Like if you're signing every message, like ChainBridge, then you've got doing a lot more signing, whereas this, you're just signing that root. So you don't have as much work to do for those attesters. Next slide, please. Thank you. And so once the signed roots are put back onto that source blockchain, and then you have relayers observe the fact that those new roots have been put onto that blockchain, and then they transfer them to destination blockchains. And because they're signed, they are trusted. And so then a user can submit a transaction with the Merkle proof and that event saying, hey, I think, you know, this is part of that Merkle tree, so you should trust it. And so that's how the cello-optic system works. There's a lot more to it. And in fact, there are some advantages and disadvantages of how they do things because of they only require one attester to sign, and they rely on having a fraud-proof window, so a time in which that root can't be used on the destination chain. So yeah, that's a complex solution with a lot more to it to what I've said, but it's that general principle though. Next slide, please. So a technology, let's go back one, thank you. So a technology that I've been working on is GPACT. And so this is a technology, we've got some example implementations. This is all open source. And this is actually a major advance in what's possible. So this technology allows you to do function calls across blockchains that are atomic. So those previous technologies that we've seen, the function happens on the source chain, but then on the destination chain, it should happen, but maybe it doesn't. You know, maybe that transaction fails. And if it does, then you've got to somehow or other fix up the, you know, the half committed transaction. Whereas with GPACT, you either everything gets committed or everything is discarded. So you can think of it as a two-phase commit scheme. And why this is really useful is, so with Solidity and, you know, Ethereum contracts, you have got your application developers, they can do composable programming. So composable programming is where you have, say, functions in contracts, and you know, one function can call that functionality that's in another contract. So it allows you to, you know, create components and then put these components together. So compose the components into a computer program, along the lines of, say, how people compose music. So you put things together. Synchronous is about when you call a function, you get the value, return value back, and you know that it's going to get executed immediately. So the programming model offered by GPACT is this composable synchronous execution model. So for application developers, it feels like they're just executing stuff within the EVM, within a single blockchain. Next slide, please. So you can imagine that you have a call execution tree that goes across multiple blockchains. And so maybe you've got some wallet, multi-sig wallet on one blockchain that talks to some blockchain which has got, say, terms of some business deal. And so it's trade finance. And so when some goods have arrived, you update the logistics blockchain. And at the same time, you want to update the finance blockchain to say that some value should change hands. And so with GPACT, you can have this complex multi-blockchain function call and spread your business logic across blockchains. Next slide, please. And so how it works is you work out what you're going to execute. So you know the entry point function calls on each of those blockchains, and you commit to the values that they're going to be when you call them on those blockchains. Next slide, please. Okay, and so let's go back one. Yep. And so you can imagine you have that call execution tree that you've committed to, and you commit to it in a start transaction. At that point, you say, this is what we're going to do. And then you execute the individual parts of the transaction, the segments of the transaction. And then once you start at the leaves of the call execution tree and you work your way up to the root of the tree. And then you execute the root of the tree, and that's going to be able to then say whether you should commit the lot or discard the lot, because it'll know whether all of the segments have worked. And if it has, then you commit your changes on the root chain and you fire off signaling transactions that will update the other blockchains. And this sort of two-phase commit scheme allows you to have provisional updates that then get committed across all of the blockchains. And next slide, please. And so looking at the system from the architecture of it, you have those different transaction types come in, and you have a cross-chain control contract, and it helps coordinate the actual call process. So the first thing is it's going to check the signatures of and proofs of various information from other blockchains. And then assuming that's correct, it's then going to call out to business logic contracts. They'll have some lockable storage. So if they do any updates, then they'll be in provisional storage. And then as well, though, that business logic, it might call out to another blockchain. So it'll actually call back into that cross-chain control contract and say, this is the call that I was planning to make with these parameters. And the cross-chain control contract can look at the expected parameters and say, yes, that matches, we're all good. Or it can reject it and say, obviously the call execution is not going how we thought it should. So we're not going to have an atomic update across chains. And hence that part of the overall transaction will fail. So that's a small taste of how the technology works. There's multiple YouTube videos and academic papers that talk about this technology. So if you want to learn more, I encourage you to have a look at that. Next slide, please. Okay, and so over to you, Weijia. Weijia, I think you're on mute, unfortunately.
Yeah, thank you, Peter. Yeah, I noticed there is a question from audience already. So I think, Peter, you may want to prepare for that question about GPAC. Okay, so we'll continue with presentation, then we'll come back with questions to answer questions. So the third topic we have is about EA CrossChain Interoperability Working Group. Yeah, and then we are going to have some of the topics here as well. We are going to talk about use cases, guidelines, and specifications. Yeah, when we started the CrossChain Interoperability Task Force at that time, and now it's a working group, we did not find many use cases for CrossChain at that time, about 2 years ago. So the first task the task force had was to come up with the documentation about the CrossChain Interoperability use cases. And I think after extensive study and discussion, we come up with 12 of them. And we published the use case document through EA, and you can look at that URL link to get it. You can also just search EA CrossChain Interoperability use case document. We can retrieve that from EA's website. Yeah, and then for use cases, we have 12 of them. I just want to mention some of them here. First, this was like almost 2 years ago, but still very, very relevant. The CrossChain DeFi, right? At that time, there are many DeFi applications, CrossChain yet, but now we see a lot of them. The asset transfer from one blockchain to another, and now from L2 to L2 as well. So that use case is very popular now. And then there's a CrossChain key management. This is a case where you can manage private keys for an institute or an enterprise with a private blockchain. And you let the private blockchain sign all the transactions. And then those signed transactions can be sent to public blockchain. This is almost like an enterprise key management system through cross-chain operation. And then there's a selective transparency and the selective privacy. We know that different blockchains may be governed by different countries, and there is a need for privacy and regulation. And in that case, the cross-chain operation may need to check which one should be passed through and which one should be blocked. And then there's cross-chain information syndication. This is a case where there are multiple blockchains, each has its own information, its own storage and data. And we can have a cross-chain mechanism to retrieve the data from different blockchains and aggregate them and put all these data in one blockchain and then present that to the users. And then there's also Oracle chain. We can make Oracle a blockchain and then use a cross-chain function to retrieve the off-chain data and then to retrieve the legacy data that's normally provided by an Oracle system. And then there's a nation state sovereign data, and we talked about that already. And then there's a cross-chain charity as well. If you can set up a charity event in one blockchain, and donors in different blockchains may contribute through a cross-chain mechanism. They don't need to transfer the asset to one single blockchain. They can just donate through this cross-chain mechanism. And there are others that's in the document. You can look at that. Okay, then go to the next one about the cross-chain criteria. And one of the most important thing is the decentralization of cross-chain. Today, many public blockchains need to be claimed as decentralized, right? And if you have two decentralized blockchain, and if you have a bridge connecting them, can you claim that cross-chain system to be decentralized? What are the things to check? So there are several things to check there. First one is, I'm using the EA-eth architecture, the layered architecture. So for the blockchain layer, we have blockchain nodes running, connecting together through boot nodes. So you need to check for the boot node to see the boot node are centralized or not. Okay, well, normally we want these boot nodes to be controlled by the community, not by a single entity. And then the consensus layer, there are several consensus. They are not centralized. For example, POA, proof of authority, BFT, those are not decentralized. And of course, you need to use POW and POS to set decentralized consensus. And that is important because you are connecting two blockchains, you are transferring assets from one blockchain to another blockchain. If one is centralized, one is not publicly secure, then there is issue if the assets are transferred to the other one. So we are going to talk about security as well with that. And then the bridge layer, right? You have relayers that transfer messages from one blockchain to another blockchain, or if relayers kind of maliciously transfer some of the message to the other chain. Right? So there should be some decentralization mechanism for that, governing system for that, and there should be a slashing mechanism for bad relayers. And then smart contract ownership. The smart contract on source chain and tax chain can be owned by a single entity, or there can be no owner for that as well. So that smart contract ownership should need to be looked at as well. And then there's Oracle decentralization. If the Oracle data is provided by a single entity, that's not much decentralized. You need to look at broader decentralization for Oracle to provide the off-chain data. And then the web services, right? If you have a centralized body to control that web service that is centralized, and you need to make sure that the cross-chain data should be a pass-through, should not be stored by that web server, or should not be altered by that web server. And of course, in the future, if there are decentralized webs coming in, that's for the decentralized. And today, at least make sure that the web services will not retain or alter the cross-chain data. Yeah, and then talking about cross-chain security consideration. Cross-chain is a holistic system, so we need to make sure source chain is secure. All the security practices that are on source chain or target chain should be followed for the cross-chain. And on top of that, there's also bridge security, and then security for various cross-chain layers. And then there should be a staking and slashing for the cross-chain operations. And sometimes randomness is introduced to increase the security of cross-chain operations. Yeah, and here just a table showing the importance of a source chain and the target chain. Sometimes the smart contract get hacked. So the security measure auditing need to be followed and the practices need to be followed. And then for cross-chain bridges, there are special things such as collusion, finality, rollback. And I think one of the questions asking about GPAC is about finality and rollback. If you have an event in the source chain and before it's finalized, then if you mint the asset on the target chain, then there is issue there. Yeah, so they do need to be trusted bridge operator, MPC, and then rotation of bridge node and slashing or slashing mechanism. And they need to be a kind of security guard on the finality and maybe capping the bridge asset transfer as well. And there's another thing, cross-chain system is very complex and we need to talk about emergency handling as well. At some point, if something goes wrong, because the bridge cannot control everything, but at the same time, things that a bridge cannot control can impact a bridge. For example, this application in the source chain get hacked, the source chain get forked, right? Get rollback. And what will happen? What will bridge do with that kind of emergency situation? So we think about several things. First one is that the capability to pause a bridge. Of course, this is in conflict with decentralization. So the security, decentralization, and the emergency handling and usability, sometimes they conflict. But we just want to put all the things here for discussion and the future specification of our cross-chain spec. So pausing the bridge is one way to do the emergency handling, and also taking snapshot of blockchain state. If something goes wrong, maybe there's a snapshot there that can help us roll back for the cross-chain operations, and then capping the bridge. Right today, if you just put 1 million onto token to secure a bridge, if the transfer of that asset through the bridge is way over the bridging amount, then there's a potential for collusion there. And then, okay, then there's also effective upgrade paths. What do we do if we need to upgrade the bridge? And then there should be a thinking about the staking and slashing mechanism as well. Yeah, and then we'll pass to Peter about scalability criteria.
Yes, scalability. It's one of those things, isn't it? So there are multiple aspects of scalability or limits of scalability. And so one of them is the bridge, and one of them is the blockchain, and one of them is the application. So working through for the bridge. So if you've got these relayers or attesters assigning every single message, rather than say a Merkle root or a block header, then you know, they're going to have to be signing a lot of messages, and that could be a limiter. And so, you know, so signing a Merkle root is going to be better. Another thing is that some of the schemes, they have the relayers coordinating to sign, and so rather than individually signing. So if you're doing that, then you've got to try and coordinate, and that coordination can take time. And so if you're trying to get to, say, 100 transactions a second, that might be difficult. Also, some of the schemes need, say, 2 or 3 or 5 transactions to be submitted on each blockchain. And so the more transactions that you're submitting, then, you know, the lower the scalability is going to be. Another thing to think about as well is, with each of these transactions actually being submitted, how much gas are they using? So gas is a proxy for CPU usage. So if you're using lots and lots of gas, then you're going to be reducing the number of transactions per second that you can do. So another concept that that Weijia talked about was limiting the amount of money on a bridge. So trying to have some sort of cap. But if you've got also some latency for money to move across the bridge, then that combination of capping the volume of money and having latency then is going to reduce the scale, how much money you can overall move across, which will reduce the scalability. So if you're using a hub blockchain, something to ask is, what's the maximum transactions per second that it can handle? Because it might become the bottleneck. Next slide, please. And so obviously, if you've got, say, a blockchain that only, say if you were using Bitcoin and it only does transactions once every 10 minutes and it only has a certain transaction rate, then that's going to affect the overall performance. And equally, say if you were using Ethereum Mainnet and you were doing some transaction there, and then just at that critical moment, there's some big NFT drop or something else, and the congestion is super high, then that's going to affect the ability to do transactions and affect your transaction rate. Next slide, please. And as well, especially for these cross-chain function call protocols, you need to be thinking about, well, what's the application doing? And so what, what code's being executed. So maybe you've got lots and lots of gas being used for some really complex code inside an application. As well, if you're using something like GPACT or another protocol that requires locking, you need to think about how have your contracts been designed, and are they designed for parallelism, or are they designed as if they're just happening in a single thread? And so essentially you need to design for parallelism so you don't have lock contention. So next slide, please. Okay, and so off to the left-hand side, you'll see that we've got an architecture that is the EEA architecture. And so as part of the cross-chain interoperability group, we worked on the architecture to the right as well and tried to come up with mapping between, in the cross-chain bridge world, what have you got that represents all these terms that we've got on the left-hand side. Now, you're going to have to go to the website to be able to read the writing, unless you've got super good eyes. But, yeah, so we've got a mapping. And next slide, please. But as things have progressed, we've come down to this 3-layer software stack for cross-chain. And so you've got applications which use function calls, which use messaging. Next slide, please. And so at the application layer, you've got applications that are cross-chain. They've got business logic across blockchains, and they need to operate across these chains. And so you can imagine that vendors could create software components that sit at this level that allow complex applications to be created more easily. And so you're going to have applications and software components at this level. Next slide. The cross-chain function call level is where you are doing your calls across blockchains. And this is the area where, say, GPAC lives, but also you've got normal, non-atomic, standard cross-function call approaches. And you've got other approaches in the middle that provide, say, some level of atomicity. Maybe they have fewer features. And so you're going to have a range of function call approaches at this level. And so the idea is that I think we're going to end up having the non-atomic approaches are going to have one interface, and the atomic approaches will have a different interface. But you can expect that you're going to have a range of function call approaches to choose between from different vendors. At the messaging layer, you're going to have, in fact, most of the technologies that exist today really operate at this messaging layer, and they're all about getting an information from one blockchain such it can be trusted on a destination blockchain. And so in the chat, we've had a lot of discussion about finality, and reorganizations of blockchains. So invariably, well, in all cases, what you need to do is before something is transferred from one blockchain to another, you need to make sure that the information is probably final. So I'm not saying completely final because for Ethereum Mainnet and proof of work chains, you've got what's called probabilistic finality. So for a IBFT, QBFT, IBFT2, so the consensus mechanisms that the EEA have helped to support and driven, they offer instant finality. So you're sure that a transaction or an event in a transaction, which is in a block, is final as soon as it's minted. For proof of work, you've got probabilistic finality. For proof of stake in Ethereum 2, you're going to have checkpoints every 32 blocks, which will give complete finality, and then probabilistic finality between that. And so, but for the probabilistic finality, say with proof of work for Ethereum 1, you can think that even if once you get to 12 blocks, 12 block confirmations, even if you had an attacker who could buy enough of those GPUs, say $1 billion worth of GPUs, they would not be able to mount, or they need to mount it. They could then mount a 30% attack, but you can't buy $1 billion worth of GPUs at the moment. And as far as trying to rent that capacity, you can rent about 1/10 of what you need on a spot market for renting hashing power. But so actually doing that is pretty much impossible. Even if the miners colluded, they wouldn't collude because the miners got a stack of ether, and if they collude, then they're going to lose a lot of money because the value of ether will go through the floorboards. So I think that we can be pretty sure that if you wait 12 block confirmations, you're pretty solid for Ethereum Mainnet. So anyway, cross-chain messaging is all about getting those events from source chains to destination chains such that they can be trusted. And so your function call layer uses those messages to create a more elaborate protocol, and then the applications use those cross-chain function calls to create yet more elaborate protocols. So it's a protocol stack with interfaces between the layers. Next slide, please. And having these clearly defined interfaces has a lot of advantages. So interoperability. So you can have a variety of applications using these implementations, the function call implementations and the messaging implementations. It gives you flexibility. So say if you've got some cross-chain system, which you've got, say across a rollup, mainnet, and some consortium chain, the message verification that you're going to want to use for each of those sources is different. And with this architecture, within the one cross-chain function call, you can mix and match which of those you're going to use. We've got infrastructure reuse as well. So say you've got some blockchain and you've got some other blockchain. So rather than you having to stand up your own infrastructure, you can use existing infrastructure. So you don't have to stand up nodes in a network. And so at the moment, you'll see a lot of these bridges, they start from scratch. They create the function call layer, they create the application layer, and they create the messaging layer, and they stand the whole lot up themselves, which is a lot of work. And so this would allow you to say, just work at your application and reuse some infrastructure. As well, you can have multiple function call layers going over the one set of, say, messaging layer, and you can have many applications using the one function call layer. Next slide, please. Another thing is that, say, some companies, they might be really good at a messaging layer piece, but they just don't have the expertise to do a good function call layer component. So that GPACT is an example where we don't have other companies doing this sort of atomic cross-chain function call layer at this point, but you can imagine others will emerge. And so having these messaging components, being able to reuse that open source component to then offer atomic cross-chain function call capability is pretty powerful. Additionally, if you're an applications company, wouldn't it be great that you don't have to create this whole infrastructure, all these components, which you might not be an expert in, and you might have, you know, hundreds of millions of dollars going over your system. And if you aren't an expert in these lower level components, then you might have done something wrong and then have the whole system open to attack. So it allows people to focus on what they're good at. And then the final thing, the advantage is, if you're a university student, if you're doing a PhD, if you're someone who's tinkering away and you want to say, well, what about if we do this? Won't life be better? Then you can do that experimentation and you don't have to create the whole stack from scratch. You can take a whole protocol stack that's available, open source, and you just plug your component in using those interfaces, and then you've got something that works. And you can then prove to everyone, hey, this is a new way, a better way of doing things. Next slide, please.
Yeah.
Okay, back to you, Weijia.
Well, thank you, Peter. Yeah. So from this point on, we are going to talk about the EA CrossChain Interoperability Working Group. And we started this about two years ago. And at that time, our justification for the task force was that we saw a growth of public and private blockchains that imposes challenges for inter-chain communication. And we think it would be good to have some working group to our task force to work on it. And also interoperability has been identified as the top takeaway with the EA survey some time ago. And then outside EA community, there have been increasing interest in interoperability as well. And we also think that just like 1990s, the internet are not connected fully, and then there's a TCP/IP that connect the internet. So we think blockchain will happen in similar way. There won't be a blockchain that dominate the whole blockchain space. There'll be a lot of blockchains, public and private, and these blockchains need to be connected. So we started the work from use cases, and we kind of accomplished some and still have some in progress. Okay, so we have a bi-weekly meeting. So you're welcome to join us. And this has been going on for 2 years. And then we also have a GitHub repository that document all the specification and guidelines that we have. All the things we discuss here are mostly in our GitHub. And then we also gather solutions from different EA member companies, for example, from Consensus, from WanChain, from Clearmatics, and other companies as well. And then we publish the use cases, and then we also do the submitted EIP 3220 for cross-chain identification specification. Today, Ethereum blockchain, we use EIP 155 to identify blockchain, but there are two disadvantages over there. First thing is that you cannot verify that blockchain ID. And second thing is that if there's a fork of blockchain, you do not know who owns that blockchain ID anymore. So EIP 3220 is to uniquely identify a blockchain, and also to be able to verify a blockchain, and also to be able to assign a new blockchain ID when the blockchain is forked into two. So you can look at that, and we're also working on the relay function specification, cross-chain discovery mechanism, and then cross-chain function call, which Peter just presented. And then we published the cross-chain security guideline, and then we also working on this cross-chain decentralization guideline that will be published soon. And we get a lot of help from EA members and also from people who work on EA, and I just put our acknowledgement there. And I saw some questions already, and then Peter and I will take those questions. Peter.
For sure. So I'll go in reverse order, because that way I can go from the bottom of the chat to the top. So there was, do I have any comments on Cartesi? They offload the VM execution to relayers and only submit ZK proof of execution to the chain for verification. Can the VM take the role of cross-chain communication and sequencing? So I think that they sound like a ZK rollup. I haven't heard of them, which is interesting that, anyway, we've got another ZK rollup system. They could probably do a cross-chain between themselves, maybe, but they're not going to probably be any good as a cross-chain bridge between various blockchains and yeah, other side chains. So yeah, oh yeah, we've got Jordan saying, yep, thanks, yeah, well, yeah. That's okay. So yeah, we had a discussion about the GPUs and renting GPUs to do hashing power, and Ben quite rightly points out that probably since my thought on how much you can buy a GPU with has gone up, so they cost a lot more now. So you're not going to be able to, even with $1 billion, you're not going to be able to buy enough of them. Look, I think it's going to be awesome when Ethereum Mainnet moves to proof of stake. So all this GPU business won't be their problem anymore. And that I think will be a massive move. So, and that's happening Q1 next year. That's my latest understanding. So it's good. So John said it's not just transaction costs, gas prices and congestion. Another problem is the value fluctuations of values. I'm not quite sure what you're getting at. If you can go off mute and quickly explain your question, then we can have a go at answering.
Hey, Peter, who was that you were wanting to explain?
That was John Sajada, rather.
Okay.
Yeah, but if you don't want to ask the question, that's okay too.
Oh, I think he may have dropped off.
Yeah. So I can see, John, that you've gone off mute, but I can't quite hear you. All right. So sorry, Weijia, go ahead.
Yeah, I think that's correct, right? Because yes, there is a fluctuation of value as well, right? The token price changes. Yes, there is a fluctuation of that when we talk about the scalability and other things as well. Yeah, that is true.
Okay, so Andreas asked about MEV attacks. So I think it's front-running attacks generally. So, so one thing you've got to watch out for in any system where you signal what you're going to do and then do it is front-running. And that's where someone gets in front of you. And so, for example, you could have an auction, and one of the function calls that you could have in the auction is bid $1 more than the last highest bid. And so that sounds like a great idea, but say in a blockchain, you put your transaction into the transaction pool and then it gets mined and put into a block. So someone else could see that you're going to spend, buy something for $1 more. And say if Weijia, does that transaction, he bids $1 more for something that I'm offering for sale, then I could quickly bid on my own thing $1 million. So then his bid comes in and says bid $1 more than the last bid, and suddenly he's bidding $1 million and $1. And so suddenly I'm selling my thing for $1,001,001. So that's in the single blockchain case. Now we've got the GPACT where we're advertising the actual call execution tree, or for that matter, any of these cross-chain protocols where you're doing a function call on one blockchain and you're emitting events saying, hey, do this on the other blockchain. You're advertising to the world, this is what I plan to do. So what you need to do is all of the normal mitigations against front-running attacks. And yeah, so and I think that's the thing you've got to watch out for, is that you are being careful with, say bidding on absolute values, for instance, or saying based on the, what I want to do is I'm saying that assuming the state is this, I will do this. And so there are, so I've got a whole stream of stuff flying through here. Weijia, do you want to have a go at responding to Andreas, who's writing a whole heap of things here?
Yeah, I think talking about the zero knowledge proof, right? Yes, we know, we talk about L1 to L2, right? And then you are optimistic and your zero knowledge roll up. Yes, we know about that, and that is important, but we do not want to say that that's the only one. I think things will move on. I think zero knowledge proof is very computation intense. So if we can trust the bridge, we can make it decentralized, and we can have a secure function call. I think we should be fine with that. Yeah. Yeah, privacy is another thing. Yeah, we know that we have selective privacy, selective transparency, and there's another question about privacy. So that is for in the use cases we talk about that, but we do not have good solution for privacy yet for cross-chain because this is a very broad topic as well. Yeah, that could be another criteria. Actually, Peter, maybe we should make privacy a criteria as well. Yeah.
Yeah, and it is something that I know at Consensus we have been thinking about it. And I think one of the things to think about is as well, when people talk about privacy, say if you're doing things across two blockchains, and say if one was the logistics blockchain and the other one's the finance blockchain, saying that the goods have arrived and then, you know, transfer this much money. So I guess that might then be signaling to people on the logistics blockchain how much the goods are worth. And then if you're passing that whole call execution tree, then your people on the finance chain know how many goods arrived. And so yeah, we've been looking at how you can say modify, have a next generation of GPACT that has some level of masking, and I think it's going to be possible. It's just not there. You know, I think that let's get GPACT working as a start, and then we can move on from there. Yeah. All right, baseline. What about baseline? And if we were in a room, I'd say, show of hands, who's heard of baseline? All right, so baseline is a technology where you use essentially, you have state on two different systems that are off-chain, and then they are able to do state updates by saying, that some transaction has happened and the new state is this, and posting a hash of the new state on chain. I think that that's boiling it down to pretty much how it works. So it's essentially, it's a zero, almost like a zero knowledge system where you don't know exactly what's happened, or outsiders don't, but then, and so you have privacy amongst, say, the people who are part of the system who are running it. So could you use this as a way of doing cross-chain? I don't think so. I mean, you could use, that would be using Ethereum Mainnet as a ordering service and so you'd be having coordinated changes across blockchains. It's a similar thing to cross-chain, but it's a bit different. And yeah. So yeah, so anyway, I think that, yeah, so I'm not sure. To me, it's not something, yeah, not something that I've considered. So we are running out of time, and I did promise that I would give Brittany the floor for 30 seconds right at the end. And so I can say maybe a good way of having the conversation here is we're going to be one, you can turn up to the meetings for the CrossChain Interoperability Working Group. Very happy to see everyone come along. Also, if you're really interested, you could, I'm sure Weijia or I would be happy to have a call at some point to have a chat about some ideas. And another mechanism would be, there's going to be a YouTube video and you can post comments on the YouTube video. Anyway, over to you, Brittany.
Thanks, Peter. And a big thank you to Weijia and Peter for joining us today. Please feel free to place your social media handles in the chat so all attendees can follow your work. For additional information about joining the EA, please reach out to membership at eea-eth-alliance.org or visit our website. You can also follow the EA on Facebook, Twitter, and LinkedIn, and those have been pasted in the chat for you. Thank you again, and this concludes today's EA Education Series webinar.
Yep, thank you.
See you later.